an application to real industry that of these confidence interval ideas comes in the form of a tolerance interval. And I go back to that underlying normal distribution, and that if we were to know what the mean and the standard deviation was of a population, we could create a specific interval two-sided by finding the associated z alpha over 2. So for 95%, then that would be a plus or minus 1.96 that we'd be using there for the z alpha over 2. Okay, well, oftentimes, though, of course, we don't have the true mean and the true standard deviation, and so that creates, of course, some different variability aspects that come along when we replace mu and sigma with x bar and s. Okay, and so one of the forms that we could look at here would be to say that x bar plus or minus some multiple of the sample standard deviation, creating a interval, either one-sided or two-sided, however we want to do that. We're interested in how that might then capture a specific percent of values or proportion of values to a particular confidence level. And we're going to go to table Roman numeral 12 for our k values that are going to get at this. And we'll take a look at that here in a moment, but first I want to pull over to the associated handout of product information and see where some of this shows up, and then we'll go grab some numbers. The handout that you have is from the Hilti product catalog, and that may not be real easy to see. So Hilti, H-I-L-T-I, and of the many products that they make, most of them are fasteners of some sort, and many of them are post-installed concrete or masonry anchors. A lot of times, after you create a concrete structure, you then want to hang certain appurtenances from that, and so how do you then go in and attach something to hardened concrete? That's the post-installed part that the concrete is already hardened. In retrofits or renovations, you oftentimes also get into this type of thing. So there's a couple of things to keep in mind, that although we're focused on this particular aspect or dimension of the problem that is on the manufacturing side, in establishing then appropriate information for then a design engineer to come along and make selections of various different types and sizes of anchors, you have to keep in mind the overall designer's model of how they're going to approach things. And one expression of that is that a notion of the factor of safety. That, for instance, there's some sort of critical value that we use for the strength of something, and then we divide that by the factor of safety, reducing that number to what we'll say, well, that's the allowable load. Right? In this particular illustration, they've used the mean of the test data, assuming that that was equal to the population sample as their critical measure. In terms of what they call global safety factors, they might be on the order of 4 to 8 for these post-installed anchors. And one of the reasons why that's so large is that the amount of variability that's associated with concrete and with post-installed anchors into concrete tends to be quite large. So we want to be further away from the edge of the cliff of problems than we might be in some other types of failure modes, where the factors of safety might be around 1.6, which is far more common in certain steel types of applications. And particularly when you get into masonry, you might have a larger factor of safety as well. The other aspect of this too is that it includes and incorporates the notion of risk, that the consequence of something bad happening tends to be in a lot of these situations more catastrophic than it might be because of the brittle aspect of the failure modes than it might be for some of the ductile type of failure modes. So that's just the kind of basic setup here that you need to keep in mind. Now, if you slide down to the bottom of that page, you'll see that they have this nice little bell curve. And so here we go. Here's this mean of the test data. And when you see ultimate load, it's not the applied load in the sense of in the application of the design environment, but rather the ultimate load is applied onto the specimens. And so this is test data of the anchors set into the concrete. So this notion here that we've got a distribution of strengths, a histogram that has a bell-shaped like set of properties to it, centered of course at the sample mean. And they're saying, well, okay, we're going to come down here to this R sub k, they call that the characteristic load, and they're going to use that as their basis from then which to divide by the factor of safety and come up with the allowable load. And the question then is, well, what should that R sub k be, given that we have a distribution that's actually centered over here, potentially at F bar. And note back up here in this label up in here that this resulting resistance is a so-called 5% fractile. So we're down here at 5% region. You could think of that as 95% one-sided, or you could think about it as 90% two-sided, even though we don't care about this upper tail aspect of things, right? And so as they take a look at this here, here's this characteristic load RK, right, for a given test series is derived from the mean, the standard deviation, and the sample size such that for 90% confidence, 95% of the loads are above the characteristic load, meaning that we've got 95% of the area is out here to the right. Right, so that's really a one-sided statement that they're working from right there. Okay, and so if we go to the next column, you'll see then the expression that they're working with. Here's their R sub k, the characteristic load, divided by V. Right, in this case, V is the safety factor. Right, and note that they're taking F bar minus K times the standard deviation. Right, the sample mean minus the sum multiple sitting here that we have yet to go find times the standard deviation. Right, notice that they've also re-articulated this in terms of the sample mean, pulling that out, 1 minus k times the coefficient of variation. That coefficient of variation, of course, turns out to be, as I've been telling you many times, important characteristic, more so than the standard deviation itself. Right? So, where the heck do they come up with this k value? Right? Now, you will note that down here below that they do talk about, for their specific case, for now the local situation, safety factors of 3 and 5, right? And you'll note that, wow, wait a minute, that's a pretty big difference in factor of safety. The larger the factor of safety in general, you're going to find that that means that the limit state is tends to be brittle, tends to be non-redundant, means more catastrophic in nature, or it might have a lot to do with the variability that's associated. Maybe there's larger variability, so to control the overall level of likelihood of bad stuff happening, they're going to go further away from the edge of the cliff. Right. So, and also before we go dive away to go grab the typical K kind of value, note that the safety factors are intended to cover the following kinds of situations in terms of the variability, but they exclude installation error. Right. So they're saying if you do it properly, there's still variability that's left over that's being accounted for in these factors of safety. So let's go find out how to grab one of these K values. Back here in page 730 of your text, in table Roman numeral 12, you have these factors for tolerance intervals. On one side, the previous side, you'll have values of k for two-sided intervals. Here on this page, we have it for one-sided intervals. Okay, and note that in this table that we end up with then the confidence level being up here, 0.9, 0.95, and 0.99, and then underneath that, the probability of coverage is down below. So we have two different probability levels, that gamma level as well as the alpha level that we're really working with. Right, so you have to be careful if you're using the one-sided interval versus two-sided interval and making sure you have the right kinds of numbers. Right, so for 90% confidence, but a 95% one side, right, now you come along and you've got a sample size and you've got the k value that goes along with it. Right, and note, and you can test this out for yourself, that as k gets real large, as sample size gets real large, then our k value is going to begin to converge to the normal value. How do I know that? Well, let's go to the 95% confidence level and 95% coverage level. Right? And note that the 97.5 one-sided, right? This is 95%, I know, so it's somewhere in between these two, right? As n gets real large, we should go to 1.96, and you're going to see that that happens close. We go past 1.96 because this is really the column that's associated with 95% one side, not the other one. So we can actually go to the two-sided and take a look. And on the facing page, or the opposite page, really, page 729, 95% confidence level, 95% probability coverage, two-sided, then once again the k value gets smaller and smaller and smaller, and as n gets larger and larger and larger. And note the size of n in terms of what large and small isn't really 30 and 40 anymore. It's much larger, and we're not quite there, right? We're starting to get closer and closer and closer, but as we go out far enough, we will get to the 1.96, because as you get large enough, your sample is becoming the overall population. Your textbook will give you a more precise numerical example of all this, but I wanted you to see where you begin to see some of this confidence interval kinds of ideas and techniques put into real practice.